everyone. Welcome into this first lecture video of the lecture series on linear algebra. We're going to start today by talking about abstract vector spaces. So the first thing we need to do is define an abstract vector space. So let's do the following. Let's let V be a set and F be a field. We don't really need to know what a field is. All right, so for us, F is either going to be the real numbers or the complex numbers. And almost the entire course, the F is going to be the real numbers, R. So for almost the entire course. So V is a set, F is a field. We need to define two more properties, all right? So these are called closure properties. These are kind of preliminary. I said two more, but really these are preliminary properties that we need to define. So closure properties. The first one, we'll call this property C1. It says, suppose the following. I'll just write this way. So let's say if X is in V, I'm going to always put like overline things that are in the set V. But if X is in V and alpha is in F, then the product alpha times X has to be in V. And so this operation is called scalar multiplication. So this property is called the closure of scalar multiplication. So I'll just write that here. And the closure property number 2, this one says if X and Y are both elements of V, then their sum, X plus Y, is in V. All right, so, and this is called the closure property of addition, or what's going to be known as vector addition. All right, so these are two properties that, by the way, are not taken for granted. Okay, we're going to have to verify that these two properties hold when we try to define our vector spaces, and that's the reason we're calling the set V is it's going to end up being a vector space. All right, so here's our definition. All right, let's let V be a set and F be a field. Again, either R or C, the real numbers or the complex numbers. And then we'll say for which the operations dot and plus, okay, are closed. So that means that is dot, which is our scalar multiplication. I'll put a dot right here and a plus right here. So dot and plus satisfy. What I really should do is put a dot right here. Okay, so there we go. So there's where the operation dot comes in. It's alpha dot x bar. So these both satisfy the properties, the closure properties, C1 and C2. All right, so this is just a starting basis. We cannot have a vector space unless we already have this. All right, so then we say the following. So then this V plus dot, this ordered triple. So this ordered triple is a vector field, vector space, sorry. It's a vector space. This is what we're defining, so I'll underline this. It's a vector space over F. Remember, we're going to be either real or complex here, so we will call them real vector spaces and complex vector spaces. But it's a vector space over F if and only if the following are true. And there are now 8 more properties. So we have to check the closure properties because that's part of this assumption right here, right? So we have to make sure that we check our closure properties, C1 and C2. They're kind of built into the definition in a sneaky way. I mean, the way I've posed it here, it's very clear, but they're built into the definition in a sneaky way. And then we have to also check if we think that our set and our operations are going to form a vector space, we have to check 8 more axioms, okay? So if and only if, I'll even write the word out. So the following axioms hold. All right, so these ones, we'll label these as A for axioms. So A1 is going to say the following. And again, these are they're going to look like statements, but we have to actually check them. But so x plus y is equal to y plus x for all x and y in our set V. All right, so this is just the commutative property of addition, right? It's the commutative property of what's going to end up being vector addition. So this has got to be true. Number 2 is going to be the associative property. So that's going to say x plus y parentheses plus z better be the same as x plus parentheses y plus z. And again, this is going to be for all x, y, and z in our set V. So associative property of addition. Number 3 is going to say the following. So there has to be, so there is or there exists an element 0 with a bar in V such that 0 plus x is equal to x for all x in V. So this one is the additive identity, right? So there is an additive identity element. That's what this one is saying. Additive identity element, which is the 0 vector, is going to end up being. All right. The fourth item is that for all x and v, so these are going to end up being vectors, there exists an element which we're going to call minus x. It's a different element though, but minus x, I'll even put parentheses, also in V, such that x plus minus x equals 0 vector from item 3. So this is called additive inverse. All right, so all of the elements in V have an additive inverse. That's what this property is. All right, number 5 starts to get the field involved. So this one says that alpha dotted with x plus y better be the same as alpha times x plus alpha times y. All right, and I'm explicitly putting the dot here. Usually we're not going to have to put the dot, but I'm explicitly putting the dot because it's been named up here, right? So this has got to be true for all alpha and f. These are going to be called the scalars, and all x and y in V. All right, the 6th property, there are 8 of these, I said that before, right? So we're getting closer, it's taking a while, but this one is very similar. This is, by the way, the distributive property of scalar multiplication over addition. All right, the next one is going to be the alpha plus beta times x. This is going to be distributive property of scalar multiplication over scalar addition as opposed to vector addition. But this one's going to say alpha times x bar plus beta times x bar, right? So distributive properties, 2 different versions, but this one's got to be true now for alpha and beta in our field F, which again is probably going to be R, the real numbers, and it's got to be true for all of our future vectors X. All right, 2 more. This last one is going to be an associative property, and it's going to say the following. Alpha times beta times x. So now notice that I've got 2 different products here, right? So this is just the product of the real numbers in this case, and this is our product of the real number with the vector. So scalar multiplication, scalar multiplication. Scalar multiplication here, just plain multiplication of numbers here. All right, this one's going to be the same as alpha dotted with beta, not dot product, but times beta times x. It's also going to be the same as, you can switch the order. All right, so putting the dot explicitly in there shows you how there's actually different kinds of products that are happening here, right? But this has got to be true for all alpha and beta and all vectors, right? All right, one more axiom. This is the last one. This one says that the scalar 1 times any vector x is just equal to the vector x. All right, this has got to be true for all x in V. All right, so these are the criteria So at this point, we have written down all the axioms that are required to define an abstract vector space. All right, so a vector space V over a field F. Again, we're just going to stick with R, so I'll stop using this F very soon. There are two different ways to approach this. Number one is you could take these as the axioms, and then you can just say, suppose I have a vector space. All right, and if you suppose you have a vector space, then you have the set V, you have the operations, and all of these axioms hold, including the closure axioms. The other possibility is that you start with a set with some operations, and then you have to check that it's a vector space. Okay, so those are two different points of view, but they're both valid. All right, so the next thing that I'd like to do is just talk about some examples of vector spaces that we've already seen. So we'll call these like examples of concrete vector spaces. But these are vector spaces that we've probably already seen in our studies up to this point. So the first one is basically the real numbers themselves satisfy all of these properties, right? So the real numbers and the complex numbers, but so the real numbers satisfy all of these. But if that was, so the real numbers are R. If that was the only space, or if that was the typical space that we were going to be studying, then we wouldn't need to make a new definition, right? We already have a definition of the real numbers. We know what the real numbers are. So the real numbers are a vector space. It turns out that the set of, say, like Rn of n-dimensional real space, right? This is also a vector space. This is a space that you might have called Vn in a calculus course. And so these are the vectors that we know how to draw, for example. So like R3, we can picture exactly what the vectors look like in R3, right? We think of them as, well, let me label this before I write anything else, but if this is our x-axis, y-axis, z-axis, we think of our vectors as arrows, right? As arrows that kind of float around in space here. But if we're going to think of the vector space itself, then really what we should do is we should put them all in standard position, right? So we have the arrows, but then to be able to add and subtract and do all these operations to them, we have to also be able to move them around, right? So we can translate our vectors wherever we want. And if we want to add two vectors, we have tip to tail method, right? We have all the different properties from calculus of vectors thought of as arrows. All right, but those are just an example of vectors that abstract vector spaces that we're going to be studying in this course. All right, so there's a couple examples that we've seen before. So these are, remember, vectors, how would you write a vector in this space, by the way? So your x with a bar, you could write in calculus, you would write something like x1, x2, x3. In this course, we're going to write x with a bar as like a vertical array, x1, x2, x3. But either one of these, as long as you have set your conventions and you know how what all the different locations mean in your notation, then either one of those is a completely valid way to represent those vectors. But like I said, we're usually going to work with these vertical arrays as our vectors when we have actual real numbers here. Okay, so another example is not just R3, right, but we know R2. So we know that we have R2, and we can also think of the complex numbers as a real vector space. So as real vector spaces. All right, so how does this work? Well, I'm going to draw two copies of the same, what look like the same space, but they're going to be slightly different because this one's going to be our real space, R2. And this other copy is going to represent the complex plane. So this is C just C1, complex numbers. And remember how this works. This is your x values and then your imaginary values here. And so if we take our geometric approach that we just thought of up here, and we say, all right, well, our two-dimensional vectors are like arrows in this real plane, right? So they're arrows in this real plane. Then we can identify this ordered pair. Let's say this ordered pair is A comma B. And so we know how this works, right? This is A, this is B. A comma B as a point, that's the terminal point. The vector itself, so I'll call this one V with a hat. That V would be AB in calculus notation, or in vertical array, it would be AB, like this, right? Well, this can all be identified if we move over to our complex numbers, can just be thought of over here, right? So here's our number. This is now A plus BI, right? And we can think of this as a real vector the exact same way. So you can think of it as an arrow over here, or you can just translate, right? As a real vector space, you can say, now this is not equal, because there are some differences here, which we'll talk about as the semester moves on, but we'll say that as a real vector space, this corresponds to the same point, the same vector, AB, as in R2. So as real vector spaces, we have this example that R2 is the same as C. Really, you should put like a squiggle here. So they're different interpretations of the same space. All right, and so to see this a little bit further, we can say a few more things about this. To see what can we do? Well, we want to add two vectors together. So so in R2, just from calculus class, remember how you do this, right? You want to add together two vectors. So let's say we have V, whose components in the calculus sense were A, B, and then let's say we have W, whose components are, let's say, P, Q, like this, right? If I wanted to add these together, right, then what do? Well, you add component by component in the calculus sense. And so you end up with A plus P here and B plus Q here, and there's your vector addition, right? What if I wanted to multiply by a scalar? So I have alpha times V. And I'm even putting the arrow on these because I'm thinking in the calculus sense, right? Well, this is alpha times A, B, and this just distributes, right? Alpha A, alpha B. All right, how's all this look in C? Well, now we have two complex numbers. Let's call them Z equals A plus BI, and W is equal to P plus QI. We want to add these together, right? So Z plus W. Well, then you just group. You just do you use your I, right? And you group your like terms. So here you have A plus P plus B plus Q times I. And notice that the I is just designating the second slot of your vector over here. It's the same as your second slot over here. All right, so just like we have here. I wrote this as a vertical, but it's the same idea, right? And then same thing, alpha times Z, well, that's alpha times A plus BI, and that's got to distribute. It's got to obey the distributive property, right? And so you notice that these two things, they are different ways of getting there, right? But they're different manifestations of the same vector space. So the complex plane as a real vector space is the same as R2 as a vector space. All right, one last example that we're used to. So I guess that's number 4. So this is a sub-item here. But these are matrices. So we've probably seen matrices in a calculus course. We're going to go back very soon and review matrices in detail. And when I say review, I mean we're going to learn more things that we haven't learned yet, right, about matrices. But these spaces are denoted. I mostly want to write down the symbol here for how they're denoted. but these are denoted by as R m by n or C m by n, like this. For the real case, it doesn't really matter for either case. These are just arrays of either real or complex numbers, so of numbers arranged. So they are arrays, but they're arranged in m rows and n columns. All right. So you just have a whole bunch of numbers in an array. Usually we put parentheses around them. And as you go, fill this out. These will all be numbers, okay? And the idea is that there's m rows and there are n columns. And so it turns out that if you add these, so they have to all be the same size, right? In terms of dimension of the array, dimension of the array. Then you just add them term by term, just like vectors, and you multiply them the same way, just like vectors from calculus. So you multiply through term by term. It basically distribute to every single term in the array. Okay? So like I said, we will review these soon. So we'll see these again soon. All right, but these are kind of what I would call the standard vector spaces that we hopefully are used to, even if we didn't know that they're called vector spaces. We're kind of we're used to them in the sense that we have seen them before, whether or not they're our favorite things or not. We have seen them before. All right, so the next examples of vector spaces are a little more exotic, and these are called function spaces. But these are going to be, in many ways, the most useful kinds of vector spaces in practice. Okay. So there are a whole lot of function spaces that obey the axioms, and we should check some of these, and you'll have exercises where you have to check, you have to verify that the axioms all hold for these function spaces. But I'm just going to write down the examples here, and we'll practice with these moving forward. So the first one is denoted by this following, by C, and then you can do any kind of interval notation here, but I'll do closed intervals AB. This is the set. So this is the set. As a set is the set of all continuous functions, continuous real functions, real valued functions, on the interval from A to B. All right? And that's the set. So that's just our V from our definition up above. We still need to define our operations, right? So the operations are pointwise addition and pointwise scalar multiplication. So I'll write with pointwise operations, and then I'll remind us what this means. All right, so let's suppose that we have two functions, f and g, in this space of continuous functions, so they're both continuous. All right, then f plus g. The function is defined if you can understand the function, right, if you know how it behaves at any point in the interval from A to B. So this function, f plus g, is defined to be the value of that function at any point x is defined to be the value of f at x plus the value of g at x, right? But then this is the element of the vector space. So this is the element f plus g in our vector space. Okay? Similarly, if alpha is a real number, now we're dealing just with real numbers, right? Then the function alpha f, right? So alpha f is now the function in here. This, when applied to x, is equal to alpha times the value of the output, f of x. All right, so it's the only way that it really makes sense, right? But this alpha f is now the element of the set of continuous functions. And so you can verify, and you really should, and you will be asked to in the exercises, but you can verify that all of the axioms hold. So I'm going to say all 10 axioms, because the closure ones are not to be forgotten, right? They're not to be forgotten. But really the other 8 are the major ones, because these operations are defined so that the closure works anyway. But verify that all 10 axioms hold for this set. All right, so that's a vector space. The vector space of continuous functions on an interval from A to B. Now you can swap out that interval for things like C from A to B when it's open, so it doesn't have to be closed on both ends. Or you could just say continuous functions on the entire real number line. So C of R, like this. All right. We can expand on that even more, because then we're going to do something like this. So we're going to say C upper n. So C to the power n. It's not really a power. It's just a notation of AB. This is going to equal the set of all functions whose nth derivative is continuous. So, first of all, we need to remember from calculus that if a function is differentiable, so if it has a derivative, then it's automatically continuous, right? So if these functions have derivatives at all, then they must be continuous. So that means that C sub n consists of things that are already continuous, right? So in other words, it's a smaller set somehow. Now, when I say smaller, these sets are huge. They're bigger than you can even comprehend. You can't imagine how many vectors are in there. They're infinite dimensional. We don't know what dimension means yet, but when we get there, these are both infinite dimensional spaces. All right? But there are less of these than there are of these, right? Because we're adding criteria that the nth derivative is continuous. But since it inherits the continuous, it also inherits the operations. So this is with the same operations as before. All right, and again, you can swap out these symbols here, but we can have C1, C2, C3, etc. You can just you can write down how many derivatives you want to be continuous, and then that will be your set, right? Now there is even one more thing we can do, and that we can write C infinity. So C infinity, you can probably guess. If Cn is nth derivative is continuous, let n get really, really big, then guess what? This says all derivatives are continuous or infinitely differentiable. You can take as many derivatives as you want or need. So all derivatives are continuous. All right. These are like, in some sense, the nicest functions that you can imagine from a calculus point of view. So these are the nicest functions in calculus. And these are the ones that, not all of them, but these are the ones that we try to find Taylor series for and stuff like that, right? Because you have to be able to take infinitely many derivatives before you can even think about having a Taylor series and a convergent series. So these are some of our favorite functions here, C infinity. And it turns out that, again, you're going to verify, but it turns out that the set of all infinitely differentiable functions forms a vector space. Okay? All right. The last example of a function space is, here I said the nicest. I'm going to amend that to the second nicest, because then what I said next was that we take these functions and we try to turn them into things that are like polynomials, right? Taylor series. So the polynomials are actually, in some sense, the nicest. So, but we're going to define those slightly differently. We know that they live here, right? The polynomials live here, but we're going to define them differently. So I'm going to write this as P sub n. And P sub n, this is equal to the set of all polynomials of degree at most n minus 1. Okay, and we'll see why we need this, why this is an n minus 1 and this is an n. So what this means then is that our polynomial, so if P is in P sub n, right, P is our polynomial, then this means that P is a function defined on, some unknown variable, we'll call it x, that can be written in the following form. It can be written as alpha, so let's call this alpha n x to the n minus 1 plus alpha n minus 1 x to the n minus 2, etc., all the way down to what? This is going to be plus alpha 3x squared plus alpha 2 x to the first plus alpha 1. It's kind of weird the way I did that, right? But this is the reason. there are, if this is the reason for having degree at most n minus 1. Remember, the degree is the highest power, right? So here's a polynomial now with terms that have the highest power on x is n minus 1, but that means that there are n of these coefficients. And the coefficients are going to be what we really care about quite a lot. There's an exercise that you're going to focus on very closely, I hope, to show that this piece of n, because of this arrangement of the coefficients are the key here, but because of the coefficients, this piece of n is similar to, in the same sense that we had before, it's called isomorphic, to our vector space Rn that we're used to. So polynomials, as far as the vector space goes, the space of all polynomials of degree at most n minus 1 behaves like n-dimensional real space. So this is kind of mind-blowing and exciting all at the same time, right? Okay. All right, at this point, we should ask ourselves, can we find a vector space or a set that fails to be a vector space? So I've just given us all these examples of sets that are vector spaces. So let's look at one that is not. So for this one, I'll call this item here example of a failure to be a vector space. All right, failure to be a vector space. So here it is. Let's let Z, so Z denotes the set of all integers. All right, so remember the integers are the numbers, so it's like -3, -2, -1, 0, 1, 2, 3, etc. All right, and we want to define some operations on these. Remember that we have to use our fields of either R or C for our scalar multiplication, all right? So the addition is going to be the usual one. So we know how to add integers, right? So the usual plus. And the scalar multiplication, though, we're going to define as follows. So the scalar multiplication, I'm going to define as like this circle operation, and here's how it's going to work. Alpha circle k is going to equal the greatest integer less than or equal to alpha times k, and that's the usual multiplication. All right, and this is true for all alpha real numbers and all integers k. All right, and so the way that this works, remember, so the way that, for example, 3.14, or just pi, right? The way this works is it knocks this down to 3, but if it was -3.14, that would knock it down to -4. So it takes the greatest integer less than whatever your entry is, less than or equal to whatever your entry is. So if you just put 3, right, then this would give you 3. All right, so this is how this works. So I'm claiming that this example is not a vector space. So why don't you take a minute to pause and ponder this yourself and tell me which axioms fail. So which axioms fail to make this a vector space? All right, now that you've had some time to think, I've written down here just the labels that we gave for our axioms. So the closure axioms work because these things all end up being integers. That's kind of the point of using this function in the first place, because it gives you back an integer here. So scalar multiplication is closed. And it turns out that all the axioms that just involve the addition are going to work. So A1 through A4 all work. And then A5, so let's scroll back up and look at this. A5 was the distributive property here, and it turns out that this one's going to work as well, right? So A5, you're going to get the same answer on both sides. It's not going to be a problem. All right, so there's A5. Now, what about A6? Well, A6, I claim, is going to fail. This is going to be one of them that fails. So this says to add first, then apply the circle, right? As opposed to applying the circle to each and then adding them up. So let's try to think of a counter example for A6. So here's one that I can think of. I'm going to put my x here prematurely before we actually test it out. But let's suppose that we have alpha equal to 1.5 and beta equal to 1.6. All right? And so it doesn't even matter what x is, because let's see what happens here. So if we do alpha plus beta first, right? Alpha plus beta first, and then times x. So there's our circle definition, right? Then this is going to give us what? We'll go our greatest integer less than function of 3.1, add them together, times x, and that just becomes 3 times x. All right? What if we do these separately, though? So alpha x plus beta x. Well, this time it's going to be 1.5 x, inside of the greatest integer function, 1.6 over here, and look what's going to happen. This is going to be 1x plus 1x. That's only 2x, right? And these are not equal, obviously. 3x is not equal to 2x, and therefore this axiom fails. All right, so once you get one of them that fails, then you can stop. But it turns out that 7 is also going to fail. So let's scroll back up. And it's for the same reason, right? 7 is going to fail for exactly the same reason. You could even use the same numbers. Okay, you could even use 1.6 and 1.5 again to show that this one fails. So I'll let you guys do that one. So 7 is also going to fail. I'll finish writing here, but then we'll leave that. So that's a failure, and it turns out 8's okay. But it doesn't matter, right? Once you get one of them to fail, then you do not have a vector space. So this is with these operations, the integers are not a vector space. So it fails to be a vector space. Okay, so it just took one counterexample there, right? To make sure that was to check that was not going to be a vector space. All right. Here's the last thing that we need to talk about in this first lecture of the course. So this one's a theorem, and we're going to prove just part of it, but here's the theorem. So the vector space axioms, there are 8 of these ones that start with an A. So 8 of these axioms are required to define an abstract vector space, but then they can be used to come up with other properties, right? Other properties of a vector space. So here are some more properties. And again, this one's called a theorem. But let's say this. Let's let V be a vector space. So now when I just say V without the operations, then we are supposed to just assume that those operations are the regular, the plus and the dot. Or you don't even need to write the dot. But we know what the operations have to be, right? We're going to use plus for addition and either a dot or just, regular notation for scalar multiplication. All right. So let's suppose that we have a vector x in V. Then here's 3 more properties that are true. So the first one, the number 0 times the vector x is equal to the vector 0. So now it's clear that it's very, very important to be careful with your bars, right? Because one thing that we don't have, and I haven't said this yet, but we don't have a way to multiply vectors by each other. So in vector spaces, you cannot multiply 2 vectors together. It's not part of the way that we built it. So this has got to be a number, right? So the number 0 times the vector x equals the vector 0. So that's got to be true. The next one says that if, and let me write this in a little more detail. So if x plus y, 2 vectors, equals the 0 vector, then y, could be either way, but let's do it this way. Y has to equal the inverse negative x. So the inverse of x. So this actually means that the inverse is unique. So the additive inverse is unique. And then the third one says that negative 1 times x is equal to that additive inverse. So another way to represent the additive inverse. Okay, remember additive, this minus sign just meant additive inverse. It didn't mean negative. I said negative, but that's just because of the symbol, right? It just meant the additive inverse of x in our axioms. All right, so I'm going to prove number 2. And then the rest of these are going to be recommended exercises. So these 2 are recommended exercises for you to do. All right, so for this one, we get to assume. So this is an if-then. So we get to assume this, right? So assume or suppose that x plus y is equal to the 0 vector. Then what conclusions can we draw? Well, then I want to somehow get this to involve minus x, right? So here's what I can write. Negative x is equal to, by axiom number 3, it's equal to negative x plus 0. You can always add 0. So this is by a3. I'll write underneath it and then skip a line. But that's by a3, right? That you can just add this, write this out as negative x plus 0. All right. And then just by substitution, if this is equal to 0, then that can be substituted in there, right? So this is then equal to minus x, the inverse of x here, minus x plus parentheses x plus y. All right, that's just by substitution, so that's not even a property. But then we can apply A2, which is the associative property, and write this as minus x plus y. So there's our associative property. And then this one right here, this is A4, right? X plus its inverse equals 0. There always exists the inverse, so this is going to be, again, 0 vector plus y. That's by A4, right? And then by another application of A3, kind of in the backwards, right? But by A3 again, this is just equal to y. All right? And these two are kind of, these two, so A3, somewhere in here we used A1, right? So I think this one is also going to use A1, because A1 says that you can change the order of these two, right? You can change the order of these two. And so, anyway, but the point here is, and you don't have to write all of these letters down as you do it, but the point is that we used only the axioms that we were given, right? And what we ended up with is, therefore, this minus x, if you just follow the equal signs all the way through, we used legal operations and we used our axioms the whole way through, we got that this inverse of x is equal to y. And so our conclusion is that, therefore, the additive inverse is unique. All right, and so whenever we end a proof in this course and beyond, you just draw a little box. Number one, we told our readers that we were writing a proof, right? We worked it out and we finished the proof, and so the box then just tells everyone that we're done. All right, and can add a little smile too if we want. But that's going to do it for this first lecture in linear algebra, and I'll talk to you guys in the next one.